All right, I'll give you a quick introduction over
All right.
here. Okay, perfect. All right, hello everyone. Welcome to our 6th general meeting. We are very happy you guys can join us today. And just a really quick reminder, next week will be our final meeting. We'll do a quarter recap and a fun social, so come out. And without further ado, we have Dr. Bronstein here to talk with us today. He's currently the director of UCLA Movement Disorders program, and I'll let him take it over.
All right. Can I share?
Of
Oh,
course.
I need, can you give me sharing permission?
Yes.
Let's see. There we go.
There
I
we go.
got it. All right. I think I found the right one. Yeah, that's the one. Well, thanks. It's a pleasure to be here. Try to keep this informal. So I'll try to leave room for questions at the end since it's hard in this format to see any questions along the way. So I'm going to talk about Parkinson's disease and try to focus on the different technologies we're using to treat it. Um, but I do have to give you a little bit of a background before, just so you know why we're doing what we're doing. So this is the obligatory intro slide, kind of showing the size of the problem. About 1 million Americans suffer from Parkinson's, and it's increasing in prevalence with time, not only because people are living longer, but as people are, since it's a disease of aging, more people are getting it. It's a huge burden, not only to patients and their families, but a financial burden to society. So a lot of the treatments that we do are hopefully to relieve some of that burden. So one of the first things that I always like to stress is that a lot of the symptoms in Parkinson's disease are really not specific to the disease itself. It's specific to the regions of the brain that are involved. So the things that set Parkinson's disease apart from many diseases is the fact that the area of the brain called the substantia nigra is involved, which releases dopamine. And I'll talk a little bit more about the neuroanatomy in a minute. But anything that injures that region of the brain will produce these sorts of symptoms, such as a rest tremor, stiffness, slow movements, decrease in facial expression, stoop posture, variety of other symptoms. So not everybody that has these symptoms have Parkinson's disease, but it's the most common cause, and but other things can do it. It is important to stress that this isn't the only parts that are involved in Parkinson's. There's a whole host of other problems. Some of it I'll talk about. They're just not specific to Parkinson's. So I'll just show you a brief video for those who haven't seen Parkinson's. So this is somebody who's had it for about 15 years, and he's without medication. Sorry, it's the quality of the video. But you can see his face has very little expression. This is what we call a rest tremor. He's just sitting there. And then when I ask him to move, the tremor goes away. So there are tremors when people are doing things or just holding their posture. We call it postural inaction tremor. And then there are rest tremors. So this is a rest tremor. It's asymmetric, which is typical for Parkinson's disease. You can see he's stooped over. He shakes when he walks, and that's actually quite specific for Parkinson's. But he takes small shuffling steps, doesn't really swing his arms at all. So that's kind of the classic Parkinson's disease. Now, most people are treated, so you hopefully won't see somebody in this state. But untreated, that's what somebody looks like who's had it for a number of years. So when I was an undergrad, this is all we knew. It's over 20 years ago. This is really all we knew about Parkinson's disease. We knew that these neurons, this is a neuron within the midbrain in the substantia nigra. The reason we know that is these areas here are pigment. and that identifies these as dopamine neurons. There are very few within the nervous system, and that's why it's called the substantia nigra, black substance. This circular inclusion here is not supposed to be there. That's called a Lewy body, and because you can see it stains with eosin, it means it's a protein. Um, and so there's this protein here. We didn't know what it was. We knew it was abnormal. We knew it was in cells that died in Parkinson's disease. So 20 years later, we've learned that that is full of a protein called alpha-synuclein. So this protein normally exists in presynaptic terminals. It's loosely associated with synaptic vesicles, has a function likely involved in synaptic transmission and recycling vesicles. It's not completely obligatory, but there are other synucleins other than alpha, so they may take over for some of the function. But the problem with alpha-synuclein is it can aggregate and become toxic. So we call that a toxic gain of function. And these aggregates come in different forms. They're oligomers, which are soluble. There's various different oligomers, but basically it's a number of alpha-synuclein molecules clumped together. And then these can form into fibrils, and this forms baited pleated sheaths. So this becomes extremely resistant and insoluble. It's hard to digest them. And this is really what forms the majority of the Lewy body. But it turns out that the oligomers are probably the toxic component. There are toxic ones and non-toxic ones, and the toxic ones are what we think leads to death. There's a variety of other degenerative diseases like Alzheimer's disease, where it's a very, very similar process. It's just the protein, and that is A beta. There also is tau, which is involved in a group of other diseases, tauopathies, that have a very similar sort of function and problems where they form these toxic oligomers, but also fibrils through beta pleated sheaths. What separates the disease is not only the protein, but where these proteins aggregate and which parts of the brain are involved. Now, Parkinson's is really interesting, at least I find it interesting, that if we look at the pathology, it probably starts in the intestines, in the GI tract, also in the olfactory bulb. And we have specimens and samples from decades before somebody actually is diagnosed with the disease, and you can see synuclein pathology here in the gut and the olfactory bulb. That, along with a theory called templating, it actually was developed, really discovered by Stan Prusner up in San Francisco, and won a Nobel Prize for this concept with prions, where a normally folded protein, in this case alpha-synuclein, for some reason gets misfolded, and when it misfolds, it starts aggregating. And these misfolded ones can interact with a normally folded one and turn this into a misfolded one, therefore self-propagating. And we think that this is occurs in Parkinson's disease, and these oligomers can then be transferred from one neuron to the next. So it actually spreads. So we think it spreads through the vagus nerve, gets into the brain stem, and it's only until it spreads into the midbrain, which is around here where the substantia nigra is, do people actually have tremors and all the things that I showed in that video. Now, it's important to know that patients with Parkinson's actually had symptoms for decades before. So they could have, many of them or most had constipation, problems smelling, olfactory bulb was very early involved, sleep disorders, which is part of the brainstem function. So, but they're not very non-specific. So you don't really know, everybody who has constipation isn't coming down with Parkinson's in decades, but most people with Parkinson's will have had that, again, decades before. So this process probably starts 20, 30, 40 years before they even know they're going to get Parkinson's disease. So as I was saying, it's really the location of the pathology which determines the symptoms. So this is kind of a simplified network diagram of the extrapyramidal system and how it's connected. This is the substantia nigra here, and that's shown here. But they project from the nigra to the putamen and the caudate. It's called the striatum. Now, dopamine is released by these neurons. And if you have some of the striatal neurons, these are medium spiny neurons, some of them have D1 type receptors, type of dopamine receptors, and other ones have D2 type receptors. The D1 receptors actually project to the globus pallidus interna directly. So we call this the direct pathway. Where the D2 project to the globus pallidus externa, then they project to the subthalamic nucleus, and then they end up in the GPI as well. The GPI sends output into the ventrolateral aspect of the thalamus, and then the thalamus connects to the cortex, prefrontal generally, and then in frontal cortex, and that feeds back into the putamen. So kind of closes the loop. D1 type receptors are excitatory and D2 are inhibitory. So what happens is if you take away dopamine, the direct pathway becomes underactive and the indirect pathway becomes overactive because you're releasing the inhibitory tone. So this imbalance is what we think responsible for the symptoms. One way we can measure this in vivo in a living person is by what's called a DAT scan. There's also a PET scan that can do a similar thing. This is where you take single photon emitters. In this case, it's an amphetamine-like compound, which binds to the dopamine transporter. The dopamine transporter sits on the presynaptic nerve terminals. So as the nigra, which is kind of south of here, projects into the putamen, which is here and here, this is the caudate. And in Parkinson's, you start losing those dopamine nerve terminals. So you can see here in Parkinson's disease, you're losing those projections into the putamen. It's an asymmetric disease for reasons we don't know. Just like in that gentleman, you saw symptoms worse on the left side. You can see that it's asymmetric dopamine loss in the brain in person. There's a PET scan that shows just about exactly the same thing. So this is a busy cartoon. I just want to make a few comments with it. So this is the dopamine neuron here, presynaptic, postsynaptic. And what happens is we're losing these terminals. There's some left, but we're losing some. And we can still make dopamine, but what limits it is this tyrosine hydroxylase. That's called a rate limiting enzyme. So when you take biochemistry, you learn about rate limiting enzymes. It actually is very meaningful for us because if I give tyrosine to a patient, it bottles up here because there's not enough tyrosine hydroxylase to convert it to levodopa. So what we do is we give levodopa and it bypasses it, and we have plenty of dopa decarboxylase to convert it into dopamine. So those remaining neurons, and probably some glia as well, have plenty of dopa decarboxylase. So we give levodopa, they can make extra dopamine to make up for the loss and reverse a lot of the symptoms. So it's quite a miracle drug. It's been around 50 years. We give it in combination with carbidopa in this country, Benzoride in Europe, and that blocks dopa decarboxylase in the liver. Liver likes to convert levodopa into dopamine as well because it has the decarboxylase activity. So we give a drug that blocks that but can't pass the blood-brain barrier. So it only does it peripherally, and that extends the half-life as well as decreases side effects. People get flush and nauseous if they don't have, if they convert dopamine peripherally, the way they used to give the drug 40 years ago. So levodopa is incredibly effective and people do really well for many years. But if you've had it for a long time, I think people have seen Michael J. Fox, there's a lot of brain plasticity. So when they give the medicine, if it gets just a little bit too high, they get extra movements. These are called dyskinesias. And you can see that these are involuntary movements. This is 15 minutes after taking a pill of levodopa. He moves much better, you can see, and he much prefer this state um, over being without the medicine the way you saw him before. We call that in the off state. But you can see that these dyskinesias can be uh, a little uncomfortable for people around to watch. People can fall from if they get too severe. I think people, again, have seen Michael J. Fox, so they've seen this before. But he walks obviously much better. Um, so what happens as people lose uh, dopamine neurons with time, the therapeutic window narrows. So early in the disease, this red bar is the blood levels of levodopa. So you take a pill and you just get a little bit in the pill, a little bit of it absorbs, and all of a sudden they feel great, reaches its peak in about 30, 45 minutes. It comes down. It's about a half-life of about 90 minutes. And by the time it gets below this therapeutic window, it's time to take another pill. So they're smooth and they do fine all day. But this narrows with time. So what happens is they take their pill and they have a short period when they feel good, but then it gets too high. And this is when they get dyskinesias. And then after about a half an hour, they feel good again for a little while before the symptoms of tremor and slowness come back. So these are called motor fluctuations, and you take another pill and up and down, going from slow and stiff to having dyskinesias to slow and stiff. So it's up and down. So much of the technology that's being developed now is really directed at treating these motor fluctuations. So we have a variety of strategies to do that. A number of them are with medications. So I showed you that carbidopa actually can increase the half-life. So can an enzyme called catechol-O-methyltransferase inhibitors. So they block the breakdown of levodopa and O-methyldopa, which doesn't cause any problems, but it just reduces the half-life. We have synthetic dopamine agonists. So these are drugs that bind to the receptors directly. The problem with those is that they don't work as well and they cause a variety of other side effects. So they're now developing new technologies in encapsulation. I think I may have a slide on this, but this is one of the newer drugs where they put in a capsule and then they encapsulate small particles of levodopa. So some are fast releasing, some are moderate release, and some are long acting, so that it increases the half-life from about 90 minutes to about 3 or 4 hours. So it's much more helpful. But now they're developing some pumps, and the first one is on the market, and I'll show you that now. Many more are being developed. And the other technology I'm going to actually spend a fair amount of time on is to talk about deep brain stimulation, since I heard this was a technology group. Okay, so this is that Rytari that I was telling you about. So these are the drugs. So Cinemed is carbidopa levodopa. So it has the carbidopa to prevent the peripherally to turn into dopamine. We can add a drug called entacapone, and the combination is called Stalevo. And so that blocks catechol-O-methyltransferase, so that increases the half-life some. So it goes, if you can see here, that the regular Cinemet is here in the bars is somewhere around 90 minutes is the half-life. So Stalevo is probably closer to 3 hours. And then Rytari, which are the encapsulated form, which has the 3 different types of coatings in them, that can increase it here all the way out to 7 hours. So it's very helpful. It's not as dramatic of a benefit as this table shows you, but it's clearly um, uh, a benefit to people. And it took a long time to develop a way to encapsulate these to make the release very slow and even. I failed to mention earlier that one of the real struggles we have is that it only gets absorbed through the neutral amino acid transporter in the gut. So that's the only place it can absorb levodopa. So if there's food around, the stomach has to empty, and then it has to um, get absorbed, and it competes with other neutral amino acids to get in. So it's a challenge for any of the oral formulations. So let's talk about some of the newer approaches for the complications. So, our motor fluctuations. So this is Duopa, which I mentioned before. There's a cartridge here that has a liquid form of levodopa that's stabilized and non-irritating. And then it's connected to a tube, and it's pumped in a tube, which is placed surgically through the stomach and fed into the jejunum in the small intestine. So this is where the highest density of the transporter is, the neutral amino acid transporter. So we program the pump and deliver it continuously throughout the day. Um, and you can see what happens to the blood levels. Unlike the pills where it's up and down, it has very stable blood levels throughout the day. And people do very well on this. It's really very helpful. The problem is people really don't like having this tube placed in their stomach, and then carrying this pump around is pretty heavy. So they're really tethered to it. So as much as it helps them, we want our patients to live a very active life, and this inhibits that. So newer technologies are being developed. So this is a smaller pump that can deliver it through a tiny needle subcutaneously. There's a couple different trials. We participated in this one and another one, which I'll talk about in a minute. But this is actually a dopamine agonist. There is one agonist which is very potent and is as potent as levodopa, and that's called apomorphine. It's unrelated to morphine, so people don't get high from it, but it can really help them. And so with this pump, we can pump it in over throughout the day, and it stabilizes people as well. Apomorphine has some side effects that levodopa doesn't have, so it's not perfect, but it's definitely very helpful and is approved. It's approved in Europe and will likely be improved in the US in 2021. We've completed our trials now. We're just waiting for them to apply to the FDA. I I did say that there was the only way to get it absorbed is through the neutral amino acid transporter. That wasn't completely true. There's an inhaled form of levodopa called Imbresia, where you can get a quick burst. So if people sometimes will take their pills, and whether they had food in there or whatever, it just doesn't work. We call them a dose failure. And they can take inhale the Imbresia, and within about 10 minutes get a pretty good blood level going. So it buys them a little bit of time until their pills kick in. So this actually took a long time to develop, and it was very difficult for them to develop it and make it safe for the lungs because it's irritating. So this is out in the market. It's not used that much, but there are some patients that really benefit from it. So varieties of different technologies to get these drugs in. So this is deep brain stimulation. So it has a variety of components. Our neurosurgeon will place, and I'll show you some pictures of how they do this, place an electrode. It has 4 contacts at the end of the electrode, you can see here. And then the wire comes out of the skull, and he buries it under the scalp, so everything is under the skin. Has a connector here with an extension, buries it under the skin again through the neck, and then implants a stimulator, which looks like a pacemaker. and it's everything is internalized. It's we do it in 2 procedures, but they're relatively short procedures. Um, and how we think this works. So years ago, when I started practicing, we didn't have DBS, but we could burn holes in the globus pallidus interna or in the thalamus, and that would improve function. We can only do it on one side, but for some reason, we thought it's helping balance the direct and indirect pathway. Uh, it turns out that if you put an electrode in there and you stimulate it at a very high frequency, anywhere usually above 125 hertz. Usually we run 125 to about 160 hertz. Um, and we can pick one of those contacts. That current there acts as a functional lesion. There are other much more, it does many more things to the neurons around it and projections, but the functional lesion is a convenient way to think about it. There's a lot of studies of local field potentials and oscillations to develop new technologies that are closed loop. Right now, we stimulate, we program it to the best we can get clinically, and then it's on all the time. The goal is going to be to feedback. So if you think about, you know, glucose monitoring, it would be ideal if you have a sensor that senses glucose, and then when you need insulin, it tells a pump, injects insulin, lowers it down. So we would love to have this, and we're very close actually to having implanted electrodes that can actually monitor these field potentials and then modulate the stimulation uh, to the different brain regions to control the symptoms. So to go back to our diagram here, we put the electrode or stimulate in the subthalamic nucleus, is probably the most popular, but we can also put it in the GPI or in the thalamus. We don't really understand, this is an oversimplified diagram. The STN GPI stimulation have very similar sorts of effects with some important differences for us clinically, but for the sake of this class, they're pretty similar. The thalamus only helps tremor for whatever reason. So we put it in any kind of tremor. We stick an electrode in the VIM of the thalamus, which is adjacent to VL, and seems to help tremor. So we think this improves the imbalance, and it improves it mostly by reducing the excessive inhibition of the indirect pathway. So we would love to be able to bring this up on the direct pathway and this down to simulate what's going on, but it turns out that it's much harder to stimulate the direct pathway. So this is just another way of showing where we put the electrode. So the surgeon will advance it and with a microelectrode, and then we can record along the way. And I'll show you some recordings in a minute. But we go through usually the trajectory. I didn't pick a very good slice. The trajectory actually goes through the thalamus. So we can hear and see white matter, that thalamic signature, and the subthalamic and the globus pallidus have their own signature. All right, so we'll show you. So this is how they do it. So this is, there's a couple different technologies that are used. UCLA uses BrainLab. So what we do is they get a very high quality MRI, and it's morphed to a standardized atlas called the Shelton-Brand Atlas. And then what happens is the surgeon measures actually with coordinates from the ACPC line. It has some very specific coordinates that they can identify, and then they correct it visually by looking at the actual MRI itself. So they're co-registered, and at the same time that these images are taken, they have uh, a frame put on so that we know where this rigid frame is, and the coordinates are then determined based on the immovable aspects of the frame. So this is what the frame looks like. This is called a Lexel frame, and this is the most common used. So when the MRI is taken, you can see these metal coordinates here and here. There's two in the back as well. These are screwed, so you just numb up the skin and you basically clamp it in. You screw it in. You have to put a little stitch in afterwards to close it, but it's very immovable. So this arc gets taken off, get the MRI with the frame on, and then you can do the coordinates are all based on calculations based on that the program that I showed you previously. So you can slide it up and down the arc for the trajectory, but they move it based on the arc and based on the positions here on the sides. So that way they get about a 1 to 2 millimeter accuracy in this. And actually we have 1 millimeter sections in the MRI, so that's as accurate as you can really get. So in the operating room, this is what we see on the right side. So it puts the atlas and starts feeding in the electrode, and you'll start seeing these cells. So up in the top here, normally what you'll see is at the very beginning, usually we start in white matter track. So you'll see something like this, which is very flat because there's no neurons, they're all myelinated fibers. Then we usually hit the thalamus, which looks like this. Every now and then you'll run into a tremor cell where you'll see these bursts. Then you go through another silent period, usually white matter, before you hit the subthalamic nucleus. We do a similar thing for the globus pallidus interna. So this is a way in the operating room that we get reassurance that we're actually in the right place. Because ultimately, once it's in there, you're not going to want to move it again. Some of the newer technologies that we're using now have, so there's 3 different companies that make it. For 20 years, we had one, Medtronic. Now, this is the second one that came out called Boston. It's St. Jude's device. And then there's a Boston Scientific. This is actually now Abbott. They changed the name. Anyway, there are 4 contacts, just as we had with the Medtronic that I showed you before, but now they're segmented. So what we can actually do is steer the current. So we can make, usually we make the active content the negative charge, and we can either do it a bipolar configuration or use the body as the ground. And normally we stimulate the whole circular part, and then you see a stimulation field that's round. But say, for example, you're a little bit off in your trajectory when you put in the electrode, and you start getting side effects if you're stimulating this side. So then you can just activate the other side, and then you steer the current away from the area that you don't want to stimulate, and then you reduce the side effects. So this is added a complexity to our programming, but gives us a lot of flexibility. So now we can not only program which of these 4 contacts, but we have the subdivisions. We also can do, obviously, the amount of current we put in determines how big the field is. We have the frequency, and we also have the pulse width, which is how long each stimulation is. So in general, our pulse widths usually run around 60 to 90 microseconds. Frequency is 125 to 160 hertz. And the current really varies considerably. Oh, here's just another way of showing current steering. So this is kind of the traditional way that we do it. But we can do all kinds of different steering currents now using these different segmented electrodes. So it's very powerful and really gives us a lot of flexibility. It's also nice that the Abbott is Mac based, so the programmers are actually very friendly, both for us and the patients have a control device that they can do certain things that depending on what we allow them to do. The newest technology is kind of going back in time because when I started, I said we used to make lesions. And the way we used to make lesions, we'd use a Lexel frame, but instead of leaving an electrode in there and using it for stimulation, we'd use a radio frequency electrode and actually burn a small hole. But that required surgery. So they developed this new technology, which is called focus ultrasound, and it's built into an MRI scanner. And the patient, in this case, they have to shave half their head, and they're put in a frame similar to the Lexel frame. And then they're put in the scanner, and this way they focus ultrasound to one spot in the brain. And usually we do this right now, it's only approved in the thalamus. And in the MRI with special signalers can actually measure temperature in the brain. So you can see where you're burning the hole, how big of a field you're burning, and have a pretty high rate of control. It's a little more dangerous than deep brain stimulation, but there are people either are not healthy enough for surgery or for whatever reason don't really want to go undergo a surgical procedure. And this is, in a sense, less invasive, even though it's making a destructive lesion. But this is the newest technology. We've had ours for about a year. It's been approved for about a year. And we've done a number of cases. Usually it's just for tremor in the thalamus. So I think with that, I can stop and take some questions.
Awesome. Thank you so much, Dr. Bronstein. That was amazing. So sorry, yeah, we have a pre-compiled list of questions that our members submitted. And if anyone else has any questions currently, you can put it in the chat. We can address them after we go through the questions we already have. All right, so one question that was really burning, we got like 5 of these, but this might take you back to when you did your fellowship and residency. And the question is, what led you to, I guess, pursue neurology and to specialize with movement disorders?
It's a good question. So it's a long answer. You want the short answer or the long answer? I'll give you the long answer. I'll give you a long answer because, so I was an undergrad at Berkeley, and I wasn't sure what I wanted to do, to be really honest. I wasn't sure about med school. I wasn't sure about anything. And I did lots of different things. And then I decided I wanted to go to med school. I thought, oh, that's going to be a good thing to do. So I was waiting. It was pre-internet and all that. So I was waiting in the advisor's office, figuring out how to do it. I wasn't pre-med. I had no idea how to apply to med school. I had all the courses, all those other things. So while I'm waiting there, I saw a poster on the wall saying, I'm looking, it was a neurologist at UCSF that was looking for a student to volunteer in a lab to work on a neurology project. So while I was waiting, I called him up and we really hit it off on the phone. And he says, what are you doing right now? And I said, well, I'm waiting for the advisor. He said, screw it. Actually, he's a 4-letter word. And come on over. So I got on my motorcycle, drove across the bay, met with him, and I started doing research in his lab. And we were studying epilepsy and drug kinetics. And so I really got turned on to neuroscience then. I actually was a physiology major and I hated neuroscience. And doing research taught me why I hated neuroscience, because there were so many things I didn't understand. And then I realized I didn't understand them because nobody understood them. So that's how I got interested in neuroscience. And then I really loved it. So I ended up applying to the MD PhD program and went into that and did my PhD in neurochemistry. While I was in med school, I was doing all my rotations and trying to keep an open mind. And I really liked internal medicine. I was really turned on by a couple of my residents that were teaching me. But then I realized along the way that I'd rather be one of those people that knows a lot about small number of things than a bit about everything. So you really need to specialize within medicine if you want to know a lot. And neuroscience and neurology really um, is a part of medicine. Really, where we deal with a lot of medical problems. So that's why I decided to go into neurology. And then you do your rotations, and then you figure out if you really like that lifestyle or not. And I didn't like the lifestyle of a neurosurgeon. Thought about it, but I liked it really hard to be a good researcher and a neurosurgeon. There are very few people that can pull it. So so now I'm a neurology resident. It was my first night on call, and I got called down to the emergency room. And they said there's very few emergencies in neurology. There's stroke, and then there's status epilepticus, or seizures that don't stop. So I got called saying, "Oh, we got this kid in status. You got to run down." So he was down there, and this kid was shaking around, but I noticed that he was awake. And anybody in status should not be awake. And so the ER attending there was about to paralyze him and intubate, which is what you do if you can't stop the seizures. He kept giving him medicine, it wasn't working. And I yelled, "Stop," convinced him to stop. I had to get my attending there and everything to stop. And what the kid had was actually this disease called dystonia musculorum deformans. He was in what we used to call it dystonic storm. And so, really, what it is a dysfunction of the basal ganglion. But reason why he got me so interested was that cognitively he was really sharp. So his story was that he had this terrible dystonia since infancy. He was from the middle, somewhere in Eastern Europe. I forget exactly where. And his parents were very ashamed of him. He never went to school. They kept him locked up, and they moved to the States when he was about 10. And he basically was locked in a room watching TV. His parents didn't speak a word of English, but he could speak English well. He taught himself English from watching TV. And I realized how smart he is. His name is Ashot. And so I became fascinated with the disconnect between motor control and cognitive abilities. And so that's what got me really interested in movement disorders. And then when you start practicing movement disorders, Parkinson's dominates the field. And it turns out to be a great field as well because we have lots of treatments that can really help. So, told you it was a long answer, but that's how I ended up where I am.
Amazing. I'm sure everyone appreciated that journey we took. Um,
So
and
the lesson is to be open, be curious, and go after it. Obviously, when I worked hard volunteering in that lab in San Francisco, I'm still in touch with him. He had a big impact on my life, and so it's going after what you're interested in, and not worrying about what other people think. Go after your passion.
love that. Um, so you talked a little bit about your undergraduate career and how you were, kind of just exploring, I would say. And you were like, oh, I'm going to get into medicine and do research. Many people also ask, like, what is the best way for an undergraduate interested in like neurological disorders, movement disorders, to learn more about them and to get, I guess, like direct experience as an undergrad?
Yeah. So it's hard, because everybody knows the system well. So it's hard, especially during COVID times. But so first you have to kind of decide, you know, what you're interested in. So if you really think you're interested more in medicine and less in research, you should pursue, I think, more opportunities inhumanity kind of things, whether it's volunteering at the Venice Clinic or whether it's teaching in South Central LA, something that you're committed to working with people if that's the reason that drives you to medicine. You know, everybody volunteers and stands in front of the hospital and greets people and those sorts of things. I personally think it's kind of a waste of time. I know you have to do it, but find an experience and make yourself available to make it meaningful and stick with it and get deeper into it. Um, do it for real and not for show. So it doesn't have to be perfect. It doesn't have to be in medicine. You, if it's in public health or something like that, something that really the reason what drives you, why you're attracted to that field, that's what you should follow. I know that everybody knows that having a good research experience is helpful to get in, but the truth is, it has to be a good research experience. You have to um, do more than just put in your hours. When you're being interviewed, like when I interview people for med school, and usually the MD PhD program, if they've done 3 years in a lab, but I can't, if they don't know more than me about the subject, it's going to hurt them. You got to you do it because you love it, and you don't do it because it's going to check off a box on your application and you think you got to get there. And if neither of those attract you, then I think you should think about another specialty, um, because it's a wonderful profession. I love it. I'm so grateful for everything I did. I wouldn't do it any other way, but it's a terrible job. And when I mean it that way is you do a lot of years of training, and the amount of time and money you have to spend to get into it. It if you look at it analytically, it's a terrible job, for the amount you get paid, the hours you work, and all that stuff. But as a career, it's wonderful. It's interesting. It's fulfilling. It's challenging. It's always changing. Um, and so I love it, and it's perfect for that. So the best advice I can give is make sure you're passionate about it. You're doing it the right reasons, um, and chase your passion. Now, the next question is, if research is interesting, how do you get in a lab? And there's just a lot of luck involved, because we get, I know, I'm listed and my lab's listed. I have a couple undergrads. It's really hard with COVID now because we're actually not supposed to have undergraduates in the lab right now, in the medical school at least. But the way those people got in my lab is not only did they were they pretty persistent in contacting me, but they didn't send out that email, "Dear Professor, I'm really interested in your research and would love to work in your lab. I'm a neuroscience student and have good grades." Those get deleted immediately. If it's, "Dear Dr. Bronstein, I really been following your research on the environmental causes of Parkinson's, and I really think zebrafish are a really cool model, and I'd love to be involved." That's the person I may, email back and talk to them. So do your homework, read about what they're doing, because we're passionate, we live it. We want people that are going to be as passionate as well. You got to remember, when you come into a lab, it takes a long time before you become useful. In other words, you're usually a negative in the lab at the first part. And because we have to train you, and then you're being taken away from the grad students, postdocs, and stuff that are teaching you. And so it takes away from them. And it takes a long time before you start being able to give back. So I'm happy if it's a wash. I mean, because somebody gave me an opportunity, and I'm very grateful, and that's why I like to give opportunities back. But you have to remember, there's often they'll come in with the attitude that we're here to serve the student. It's not like the classroom, where the classroom is there to serve you. We're here to serve patients with Parkinson's, the National Institute of Health that funds our support, and all the other funds. So that's our job. our first job and our second job really isn't to teach undergrads. Um, but we enjoy doing it because people gave us that effort and all that. So you have to go in with that attitude that it is an opportunity. Um, and almost in any lab I know, if you take that opportunity seriously and you really work hard and you learn above and beyond what's asked of you, people will give you as much as you ask. So I've had undergraduates end up with first author papers in really strong journals because they were just so committed, um, that that they just saying they wanted more. They came with ideas and that sort of thing. So that takes a while to that it takes a while to get there. She had been in the lab for a year before she was able to get to that point, saying, "I'm really interested in doing this." So if you're persistent, and it doesn't have to be exactly what you're interested in as well. It's learning how to do science, learning how to work with other scientists. That's what you want to do. Now, the advantage of doing that is not only are you growing and contributing, but you get to learn whether you want to do that. It's great. I'm very happy if a student comes in my lab and does a great job and says, you know what, I really enjoyed it. I loved it, but I still really rather be a doctor than be a scientist. That's great, and that's the way you learn how to do it. You wouldn't learn it if you didn't do it another way. And those people often will shadow me at times in clinic or when I'm on the wards, so they get those experiences as well, and we work together. Um, but the one factor is don't just check the boxes, put in the time. Um, it's not going to serve anybody well. It's not going to get you into med school. You're going to lose time. Um, so do what you're interested in and what you're passionate about. That's what's going to make you stand out. Everybody looks at the stats and they say, "Oh, biochemistry major is the number one major that gets in, or neuroscience. So I'm going to do that." And then, "Oh, they worked in a lab, so I'm going to do that." And then I'm going to, volunteer at the hospital. So you check all the boxes. I can tell you that this will depress you, but there's over 1,000 students with 4.0s that have done all those things applying to med school for 150 spots. So doing those things do not make you stand out in the crowd. What makes you stand out is by really getting into one thing and doing it well. And that's what you need to do to stand out. Obviously, the grades and MCATs, you have to do well. And I always tell the students that is that don't sacrifice your grades for this. We'll make accommodations around tests and things like that because you need to have good grades to get in. We realize that. But that's the way you stand out. And when you interview, you can talk their ear off about the science and how excited you are about it. And that will impress every interviewer, guaranteed. Other questions?
Wow, that was amazing. Woo. I'm sure all of us pre-med students out here appreciate all of that advice, especially with COVID and trying to stay involved with virtual learning. I guess
Yeah.
sorry, go ahead.
I was just going to say it really is a struggle with COVID, and I don't have any great answers for that. Yeah, it's a problem.
Oh yeah.
I don't know if you can get involved even in tutoring or, things like that. Any way you can help, find some way that you can help. But got to be creative because we're all new to this. Nobody knows how to do the pandemic. So,
Oh yeah, very true. And I'm sure telemedicine will also change quite a lot in the future.
oh yeah, we've had the technology. I do it all the time. I sit in the same seat and see patients in my clinic. I do mostly telemedicine now. So we can do most things through telemedicine. It's quite helpful. And then there's a lot of very cool technology, wearable devices and things like that that do a lot of home monitoring now. So we have devices. It's a watch light thing which has accelerometers, but it measures tremors and slow movement and dyskinesias over a 7-day period. It uses AI to figure it out, and it gets sent. The report gets sent to me, and I get a 7-day diary on the patient without anybody having to do anything. So you'll see more and more of that about that's coming around, and this is actually really helped. COVID has helped that. We've had the technology, but everything runs on money, and insurance companies and Medicare wouldn't pay for telemedicine before. So then they did, and they probably will continue because it's very helpful. You can imagine older people don't have to drive to come in. So it's very helpful for them. Or if there's specialists, I'm a subspecialist. There aren't enough of us around. So I see people from all over the country. We can just do it by Zoom now.
Wow, you actually, okay, that was one of the questions I was going to ask right after. But you talked about, tracking the tremors, keeping that diary, having it sent to you, the doctor. And actually part of our club here, we have an innovation team working hard to create a prototype of one of my patents, which uses like miniaturized gyroscopes, essentially in a hand glove to help stabilize essential tremors in PD patients. So I guess what are further thoughts of using external devices to complement the biological treatments that we have?
Yeah, so the measurements have been much more easy to deal with, and so it's actually on the market now. If you look up Global Kinetics, they have a product out. We actually did some studies with them to validate that it works. The devices that have been used, there are devices out there, stimulation and that sort of thing, to overcome tremor, and they've been of limited value so far. Part of the problem is the device itself may stop the tremor, but then your hand is kind of in a glove with the device, so you've lost the dexterity and all that stuff. So there are people working on it. It sounds like you have something very interesting. So it's hard to know. We don't even know, where the oscillator is. We think they're central, at least in essential tremor and in Parkinson's disease. So how do you alter that central oscillator peripherally? It's tricky. So I'd be interested to hear what you have at some point. So.
Awesome. Well, thank you so much, Dr. Bronstein. We don't want to take up too much of your time. If you could stay back for 10 more minutes, we did receive a couple more questions, but if not,
All right. Yeah. How about one or two more questions?
Sure. RT, how about some research questions or further questions?
Yeah, I know Georgia put a question in the chat related to like the DBS system that you talked about earlier.
Yeah.
And that's just one question we wanted to ask you. So in regards to the closed loop DBS system, how is it that the electrode is capable of detecting the local electric potentials?
Yeah. So, the technology is beyond me, to be really honest. We already have, so there are systems that have been devised that actually have separate electrodes that measure at one place and feed back to the stimulation. But actually the ones right now, the Medtronic ones, actually can measure, some of the contacts actually measure field potentials even during stimulation. And I really honestly can't figure out how they do it. So right now, this technology is already available. We're implanting them where we can measure it. It's not that useful. It's not useful at all, honestly, right now, but they're planning on using it to feed back. So normally we're the field potentials are in the beta range, and then they go to gamma range when we move. And in Parkinson's, we lose a lot of the gamma field potential. So the idea is to try to replicate that. It's been of limited success. There's a ton of work has been involved. I'm probably not the best person. I'm more of a molecular biologist than I am a electrical engineer. But that's basically the basic thought process.
Yeah, that's really interesting, Giorgio. I hope that helped you. That's definitely something that like is really interesting these days with like the whole connection between neuroscience and physics is something that like is really interesting to think about.
Yeah, and there's a bioengineering people. We used to have a bioengineering program, but there are bioengineers around. There's some physicists that work with our neuroscience researchers. So there's one of the nice things about having a medical school on the same campus as the undergrad is there's a lot of collaboration with some of the real hard science labs, which is great, engineering, etc.
And then just kind of our last question for today. In your career, how do you maintain the balance between clinical practice and research?
So that's you don't. That's the easy answer. People ask how I split my time, and I say, well, I do 50% clinical, 50% research, 50% teaching. So it's hard, and it's getting harder. I will tell you, most people that have a basic science lab nowadays do 90% basic science and 10% clinic. Very little teaching other than clinical teaching, or the opposite, they spend most of their time in the clinic and may do some clinical trials or some teaching on the side. I'm unusual. I do a little bit more. I do clinical work, probably a little less than half the time, though it creeps in because I really enjoy it. And I enjoy working with people, but I like the lab as well. So I have a relatively small lab. I have about 6 people. I try to keep it about that size, 6 or 7 people. And we do more focused studies and do a lot of collaboration. So that's why I got out of using mice. I used to make transgenic mice, but it just takes up your life trying to keep them fed, just they're expensive, and keeping the line straight, and it's very expensive. So then you're writing grants all the time, and so it becomes harder and harder. Probably the best advice I got was when I was a MD PhD student, and one of the professors, he was from Yale, he said, one of the things that we're at a disadvantage because we have to spend a lot of time on clinic, but we have the advantage that we have a greater insight into the disease than PhDs do. And I think that's true. So we have to be more creative because we are competing. I'm a half-time researcher competing with a full-time researcher for grants and papers. And then lower your expectations. I'm not going to win a Nobel Prize. I'm fine with that, as long as I contribute and it's interesting and fun. I contribute to the field. I contribute to education, to my grad students and postdocs and undergrads. That's satisfying for me. But if you're a bit more ambitious and you want to achieve higher, then you focus more on the research. So I think everybody has to find their own balance, and it is different for everybody.
Well, thank you. Yeah, that was a really complete answer to that question. Really helpful.
So anyway, it's been fun. If you have questions, you can shoot me emails. Try to answer them right away if I can, if not too many. I hope it's helpful. And I wish you all good luck. In the medical school one of these days.
All right. Thank you so much, Dr. Bronstein.
Thanks for having me.
Thank you.
Bye-bye.
Pleasure. See you. All right. Thank you guys for staying longer. I hope this was very helpful. I know when he was talking about the medical school, it's like, wow, Very impressive. But yeah, thank you guys so much for coming to our second guest speaker event. And I hope to see you in our last meeting of the quarter next week. Should be more fun, relaxing. We'll play some games to de-stress for finals. But yeah, thank you everyone. Thanks for coming.